Tonight we will explore the exact moment our sun will leave its stable state and begin transforming into a red giant, a process that will reshape the entire solar system. We'll follow how the sun works today, the slow internal changes already underway, what triggers its expansion, how large it will become, and what ultimately happens to Earth as conditions break down long before that final stage. Everything that follows is already set in motion. If you enjoy these calm science explorations, please consider liking and subscribing to the Deep Sleep Discoveries channel. We begin with the sun as it exists right now, and why its stability will not last forever. The sun is approximately 4.603 billion years old, formed from the same collapsing cloud of gas and dust that produced the Earth, the Moon, and every other body in the solar system. That cloud compressed under its own gravity until temperatures and pressures at the center became sufficient to ignite nuclear fusion, a process that has continued without interruption ever since. The sun and Earth did not form in sequence. They formed together from the same material in the same event, and have been gravitationally bound to each other for the entirety of their existence. The sun is classified as a G-type main sequence star, a category sometimes called a yellow dwarf, though that label is misleading. The sun does not appear yellow from space. It emits peak radiation in the blue-green portion of the visible spectrum, but because it radiates broadly across all visible wavelengths, those frequencies combine to produce white light. The golden appearance of the sun as seen from Earth is an atmospheric effect. Rayleigh scattering in Earth's atmosphere filters out the shorter blue wavelengths during most daylight hours, leaving the longer reds and oranges. Viewed from outside the atmosphere, the sun would appear as an intensely bright white source of light. The sun's diameter is approximately 1.39 million kilometers. Roughly 109 Earths could be lined up side by side across that span. By volume, approximately 1.3 million Earths could fit inside the sun. These figures place the sun in the middle range of stellar sizes. It is not among the largest or smallest stars in the galaxy. Within the solar system, however, it accounts for the overwhelming majority of all mass present. Every planet, moon, asteroid, comet, and grain of interplanetary dust combined represents a fraction of the sun's total size. Temperatures at the sun's core reach approximately 15 million degrees Celsius. At those conditions, matter exists as plasma, a state in which electrons are stripped free of atomic nuclei and all particles move at velocities sufficient for nuclear reactions to occur. Hydrogen nuclei, which are single protons, collide frequently enough and with enough energy to overcome their mutual electromagnetic repulsion and fuse into helium. That fusion process releases energy which exerts outward pressure and counterbalances the inward force of gravity. The balance between these two forces has kept the sun in a stable state for 4.6 billion years. Every second, the sun converts approximately 600 million tons of hydrogen into helium through nuclear fusion. In that conversion, a small fraction of the total mass, roughly 4 million tons per second, is released as energy in accordance with Einstein's mass-energy equivalence. This rate of consumption has been sustained continuously since the sun ignited, and the sun contains enough hydrogen in its core to maintain it for approximately another 5 billion years. The current phase of the sun's life is not approaching its end. By most measures, the sun is roughly at the midpoint of its main sequence lifetime. Energy produced in the sun's core does not travel directly to the surface. The solar interior is dense enough that photons of light are continuously absorbed and re-emitted by surrounding particles, undergoing a random walk through the radiative zone that can take between 10,000 and 170,000 years before the energy reaches the outer convective layer. By the time that energy arrives at the photosphere and escapes into space, it has been transformed and redirected thousands of times over. The sunlight that reaches Earth today was generated deep inside the sun long before recorded human history. Once solar energy exits the photosphere and enters space, it travels the 150 million kilometers to Earth in approximately 8 minutes and 20 seconds, moving at 299,792 kilometers per second. That transit, which takes less than 9 minutes, covers a distance that would require more than 160 years to drive at highway speed without stopping. The contrast between the tens of thousands of years that light spends moving through the solar interior and the 8 minutes it takes to cross the distance between the Sun and Earth illustrates how much of the delay occurs within the star itself, not in the space between. The Sun's outer visible layer, called the photosphere, has a surface temperature of approximately 5,500 degrees Celsius. At that temperature, the photosphere emits white light across the full visible spectrum. The warm golden tones associated with sunlight on Earth result from the selective filtering of shorter blue wavelengths by Earth's atmosphere, not from any property of the Sun's surface itself. The photosphere is not a solid surface. It is the layer at which the solar plasma becomes transparent enough for light to escape directly into space, and it is in constant convective motion with rising and falling columns of plasma several hundred kilometers in diameter. The Sun contains 99.86% of all the mass in the solar system. The combined mass of all 8 planets, their moons, the asteroid belt, the Kuiper belt, and every other object in the solar system amounts to less than 0.2% of the Sun's mass. Jupiter, the largest planet, accounts for the majority of that remaining fraction. The gravitational dominance implied by this mass distribution is total. Every object in the solar system at every distance follows an orbit determined primarily by the Sun's gravitational field. The planets do not orbit a common center so much as they orbit the Sun with minor perturbations from each other. The Sun's gravitational influence extends approximately 2 light-years in every direction, forming a sphere within which no other star's gravity dominates. The outer boundary of this region roughly coincides with the estimated outer edge of the Oort cloud, a vast diffuse population of icy bodies thought to orbit the Sun at distances between 2,000 and 100,000 astronomical units. Comets that appear in the inner solar system are generally understood to originate from this region, perturbed out of their distant orbits by gravitational interactions with passing stars or the galactic tide and drawn inward over timescales of millions of years. The Sun does not rotate as a rigid body. Its equatorial regions complete one rotation approximately every 25 days, while its polar regions take closer to 35 days. This differential rotation occurs because the Sun is composed of plasma rather than solid material, and different latitudes are free to rotate at different rates. Over time, differential rotation wins and distorts the Sun's magnetic field lines, increasing their tension and complexity. That buildup of magnetic stress is the primary driver of solar activity events, including solar flares and coronal mass ejections, which tend to increase in frequency as the magnetic field reaches peak complexity near solar maximum. The Sun's magnetic field extends well beyond the orbit of Pluto, forming a region called the heliosphere, a bubble of solar wind and magnetic influence that separates the solar system from interstellar space. Within the heliosphere, the outward pressure of the solar wind holds back the incoming flux of galactic cosmic rays, high-energy particles produced by supernovae and other energetic events elsewhere in the galaxy. The boundary between the heliosphere and interstellar space, called the heliopause, was first crossed by Voyager 1 in 2012 and by Voyager 2 in 2018, providing the first direct measurements of conditions at the edge of the Sun's magnetic domain. Solar flares are sudden releases of magnetic energy from the Sun's atmosphere, produced when stressed magnetic field lines reconnect and discharge stored energy as radiation and charged particles. The largest recorded solar flare events can release energy comparable to billions of hydrogen bombs within seconds. The most powerful solar storm in the historical record, the Carrington event of 1859, induced electrical currents strong enough to cause telegraph equipment to catch fire and to produce aurora displays visible as far south as the Caribbean. A comparable event affecting present-day electrical infrastructure would cause widespread disruption to satellite systems, power grids, and communications networks. The solar wind is a continuous outflow of charged particles, primarily electrons and protons, emitted from the Sun's outer atmosphere and traveling through the solar system at speeds between 400 and 800 kilometers per second. Unlike terrestrial wind, it carries no physical sensation and cannot be detected by human senses. Its effects, however, are measurable across the entire solar system. The solar wind shapes the tails of comets, which always point away from the Sun regardless of the comet's direction of travel. It compresses Earth's magnetic field on the side facing the Sun, and stretches it into an elongated tail on the night side. When charged particles from the solar wind are directed by Earth's magnetic field toward the polar regions, they collide with molecules of oxygen and nitrogen in the upper atmosphere at altitudes between 100 and 300 kilometers. Those collisions excite the atmospheric molecules, which then release the absorbed energy as visible light. The result is the aurora borealis in the northern hemisphere, the aurora australis in the southern hemisphere. The specific colors produced depend on which atmospheric gases are involved and at what altitude the collisions occur. Oxygen at higher altitudes tends to produce red, oxygen at lower altitudes produces green, and nitrogen contributes blue and purple tones. Beyond the photosphere, the Sun has an outer atmosphere called the corona, which extends several million kilometers into space and reaches temperatures between 1 and 3 million degrees Celsius, hundreds of times hotter than the photosphere below it. By conventional thermal physics, a gas should not be hotter farther from its heat source, and this inconsistency has been a subject of active research for decades. Current leading explanations involve the dissipation of magnetohydrodynamic waves and the cumulative effect of small-scale magnetic reconnection events called nanoflares. Neither mechanism has been conclusively confirmed as the primary driver, and coronal heating remains one of the significant unresolved problems in solar physics. Sunspots are regions on the photosphere where strong, concentrated magnetic fields inhibit the normal convective rise of hot plasma from below, resulting in a localized drop in surface temperature to approximately 3,500 to 4,500 degrees Celsius. Because they are cooler than the surrounding photosphere, they appear darker by contrast. Individual sunspots can span distances larger than Earth's diameter. Sunspot activity follows an approximately 11-year cycle, alternating between periods of low activity, solar minimum, and periods of higher activity, solar maximum, during which solar flares and coronal mass ejections become more frequent. The pattern has been documented through telescopic observation since the early 17th century and is detectable in geological records extending back much further. The Sun is currently in the main sequence phase of stellar evolution, the long, stable period during which a star generates energy by fusing hydrogen into helium in its core. Main sequence stars are the most common type in the observable universe. For stars in the Sun's mass range, the main sequence lifetime spans roughly 10 billion years. The Sun entered this phase approximately 4.6 billion years ago and is estimated to remain in it for approximately 5 billion more. The main sequence is defined by a stable equilibrium between the outward pressure of nuclear fusion and the inward pull of gravity, an equilibrium that has held for the full duration of the Sun's current lifetime. The Sun is considered a third-generation star, meaning the heavy elements within it, carbon, oxygen, nitrogen, iron, and others, were not produced by the Sun itself during its current lifetime, but were synthesized in earlier generations of stars that lived and died before the solar system formed. The universe began with primarily hydrogen and helium. Heavier elements are produced through nuclear fusion inside stars and dispersed into the interstellar medium when those stars end their lives. The cloud that collapsed to form the solar system already contained those heavier elements inherited from prior stellar generations. The calcium, iron, and carbon present in every living organism on Earth were produced inside stars that no longer exist. The Sun is located approximately 26,000 light-years from the center of the Milky Way galaxy and orbits the galactic core at a speed of roughly 230 kilometers per second. A single orbit takes between 225 and 250 million years, a period sometimes called a cosmic year or galactic year. The Sun has completed approximately 18 to 20 of these orbits over its lifetime. The most recent time the Sun occupied its current position in the galaxy, the Triassic period, had just begun and the earliest dinosaurs were appearing on Earth. The orbit before that corresponds to a time before complex animal life had fully diversified. The Sun is approximately 30% more luminous today than it was when it first ignited 4.6 billion years ago. This increase has been continuous and gradual, accumulating over timescales far too long to observe directly. It is a consequence of the Sun's internal composition changing as hydrogen is converted to helium, a process that alters the structure of the core in ways that increase overall energy output over time. The brightening is not a future event. It has been happening throughout the Sun's entire life and is ongoing at this moment. As nuclear fusion converts hydrogen into helium in the Sun's core, the helium accumulates rather than dispersing. Over time, this changes the core's composition from nearly pure hydrogen to an increasing fraction of helium. Helium nuclei carry more charge than hydrogen nuclei and do not fuse under the current core conditions, so they contribute mass without contributing energy production. The gradual buildup of this inert helium is the starting point for the sequence of structural changes that will eventually drive the Sun off the main sequence and into the red giant phase. Helium is denser than hydrogen, and as it accumulates in the core contracts under gravity. That contraction increases the pressure and temperature in the surrounding hydrogen-burning region, which in turn increases the rate of fusion there and raises the Sun's total energy output. This feedback relationship, accumulated helium leads to core contraction, which leads to increased shell temperatures and higher luminosity, is the mechanism behind the Sun's gradual brightening over its lifetime. It operates continuously and will continue to do so until the available hydrogen fuel in the core is sufficiently depleted to trigger a more significant structural change. As increasing energy flows outward from the Sun's compressing core, the outer layers receive more energy than before and expand slightly in response. The Sun's radius today is marginally larger than it was several billion years ago. The expansion is so gradual that it is undetectable over any human timescale, but it is real and measurable in the context of stellar evolution models. This slow outward growth of the Sun's radius is an early manifestation of the same process that will eventually produce the dramatic expansion of the red giant phase, the difference being one of degree and rate, not of underlying mechanism. In approximately 1 billion years, the Sun will be roughly 10% more luminous than it is today. That increase in solar energy output is sufficient to raise Earth's average surface temperatures to a point where the global water cycle becomes significantly more intense. Evaporation rates increase, water vapor builds up in the upper atmosphere, and the conditions that have supported complex life for hundreds of millions of years begin to shift. The change will unfold over millions of years, not suddenly, but the direction is established by the physics of the Sun's internal evolution and will not reverse. Within approximately 2 billion years, the Sun's increasing output is expected to push Earth past the inner edge of the habitable zone, the range of orbital distances at which liquid water can persist on a planetary surface. As surface temperatures rise and water vapor accumulates in the upper atmosphere, solar ultraviolet radiation will break down water molecules, allowing hydrogen to escape to space. Over millions of years, Earth's oceans will lose volume through this process. The loss will not be abrupt. Liquid water will become progressively less abundant at the surface as the planet gradually moves outside the range of conditions that have defined its habitability for billions of years. In approximately 5 billion years, the Sun will have converted roughly half of the hydrogen available for fusion in its core. At that point, the depletion becomes sufficient to disrupt the equilibrium that has defined the main sequence phase. The core can no longer sustain fusion at the rate required to counterbalance the inward pressure of gravity. This threshold marks the beginning of the transition away from the main sequence. The Sun will not abruptly change at this point. The shift will be gradual, but the internal balance that has held for billions of years will begin to break down in a way that sets the subsequent chain of events in motion. As hydrogen is depleted in the Sun's core, the primary site of fusion migrates outward into a shell surrounding the inert helium core. This phase, called shell hydrogen burning, occurs when temperatures and pressures in the region just outside the exhausted core become sufficient to sustain fusion. The core itself, no longer generating energy, begins to contract under gravity. The shell surrounding it burns with increasing intensity as the contracting core below raises local temperatures further. Energy production has effectively moved from the center of the star to a shell around it, and that geometric shift has significant consequences for the structure of the entire star above. Shell hydrogen burning is less stable than the core fusion it replaces. Energy output from the burning shell is not constant. It varies in response to the evolving conditions of the contracting core below and the expanding envelope above. These fluctuations propagate through the Sun's outer layers, causing them to expand and contract slightly in response. The steady, consistent energy output that characterized the main sequence sun begins to give way to a more variable pattern. The outer atmosphere of the star starts to respond to an energy source that is both stronger and less uniform than the one it had relied on for billions of years. The inert helium core, no longer supported by fusion pressure, contracts under gravity. That contraction converts gravitational potential energy into heat, which flows into the hydrogen-burning shell above and intensifies its fusion rate. The shell generates more energy, which pushes the outer layers further outward, which in turn reduces the pressure on the shell and allows it to expand and cool momentarily before the contracting core heats it again. This cycle, contracting core, heating shell, expanding envelope, does not stabilize. Each iteration drives the outer layers a little further out and the core a little further inward, accumulating toward the eventual red giant configuration. The progression from a hydrogen-burning core to shell-burning and eventual red giant expansion is not triggered by any external event. It follows directly from the laws governing nuclear physics and gravity as applied to a star of the Sun's mass and composition. A main sequence star consuming hydrogen will inevitably exhaust its core supply, shift to shell burning, and begin expanding its outer layers. The timeline varies with stellar mass, but the sequence is consistent across all stars in this mass range. The Sun's future trajectory is not a prediction so much as a direct extrapolation of its current physical state. The transition from the main sequence to the red giant phase unfolds across hundreds of millions of years. No individual moment or event marks the boundary between the two states. The change in the Sun's internal structure is continuous, with each stage following from the previous one without interruption. From an external viewpoint, from another star system for example, the transformation would be undetectable across a human lifetime, a civilization's lifetime, or even across the span of recorded geological time. Only measurements made across millions of years would reveal that a change was occurring. During the transition from the main sequence to the red giant phase, the Sun's total luminosity will rise substantially. As shell hydrogen burning intensifies and the outer layers expand, total energy output climbs from its current level to tens, then hundreds of times its present value. This increase does not occur at a constant rate. It accelerates as the internal structural changes compound over time. The inner solar system will receive progressively more radiation over hundreds of millions of years, far in excess of what any planetary atmosphere or surface chemistry could compensate for through natural feedback mechanisms. As the Sun's outer layers expand, they cool. In stars, surface temperature and color are directly related. Hotter surfaces emit light weighted toward blue wavelengths. Cooler surfaces emit light weighted toward red. The Sun's photosphere currently sits at approximately 5,500 degrees Celsius, producing white light. As expansion cools the outer layers, the peak emission wavelength will shift toward longer, redder wavelengths. The Sun will not change color instantaneously. Over millions of years, its visible color will drift from white through yellow-orange towards the deep red associated with giant stars at surface temperatures of 3,000 to 4,000 degrees Celsius. A red giant's surface temperature is lower than the Sun's current surface temperature, not higher. The color red in a stellar context indicates cooling, not heating. A red giant's high luminosity does not result from an extremely hot surface. It results from an extremely large surface area. A star with hundreds of times the Sun's current radius has hundreds of thousands of times the Sun's current surface area, and even at a cooler temperature, it radiates an enormous total quantity of energy. The red giant Sun will be both larger and cooler at its surface than the Sun is today, and vastly more luminous overall. Long before the Sun enters the red giant phase, the increasing solar luminosity will accelerate a process already occurring in Earth's upper atmosphere, the photodissociation of water vapor by ultraviolet radiation. Water molecules broken into hydrogen and oxygen in the upper atmosphere can lose their hydrogen component to space through thermal escape, a process called hydrodynamic escape or atmospheric erosion. As the Sun brightens, this process will intensify. Over hundreds of millions to billions of years, Earth will lose a progressively larger fraction of its hydrosphere through this mechanism, independent of and well in advance of any direct effects from the red giant expansion itself. Earth currently maintains a long-term climate regulation mechanism called the carbon silicate cycle, which ties atmospheric carbon dioxide concentrations to surface temperature through the weathering of silicate rocks. When temperatures rise, weathering rates increase, drawing more carbon dioxide out of the atmosphere and reducing the greenhouse effect. When temperatures fall, volcanic replenishment of carbon dioxide over geological time counteracts the cooling. This cycle has moderated Earth's climate across billions of years despite gradual changes in solar output. As the sun's luminosity continues to increase, however, the incoming energy will eventually exceed what the cycle can offset, and the regulation mechanism will no longer be capable of maintaining surface temperatures within the range that has supported complex life. Planetary scientists describe a moist greenhouse state as a condition in which water vapor accumulates in a planet's upper atmosphere in sufficient quantity to substantially amplify the greenhouse effect, triggering a self-reinforcing warming cycle. Venus is understood to have undergone a comparable transition at some point in its history. Its current surface temperature of approximately 465 degrees Celsius and its dense carbon dioxide atmosphere are consistent with a world that lost its surface water through a runaway greenhouse process driven by proximity to a brightening star. Earth's trajectory under continued solar brightening is expected to follow a similar path, with the timeline determined by how quickly the sun's luminosity increases relative to Earth's climate feedback capacity. The sun's gradual brightening is one of the primary constraints on the long-term habitability of Earth's surface. Astrobiological models that calculate how long Earth will remain within the sun's habitable zone account for this brightening as a central variable. Estimates for how long Earth's surface can maintain liquid water range from roughly 1 to 2 billion additional years, depending on assumptions about climate feedback mechanisms and the definition of habitability. The timescale for a recognizable complex biosphere, one involving plant life, animal life, and the full ecological systems that characterize Earth today, is shorter than that, with estimates generally falling in the range of several hundred million to about 1 billion years from the present. Lunar rocks collected during the Apollo missions contain records of the early solar wind embedded in their surfaces. Because the Moon lacks a significant atmosphere and has no active geological processes to recycle its crust, ancient solar wind particles implanted in lunar regolith billions of years ago have been preserved. Analysis of these samples has provided data on the intensity and isotopic composition of the solar wind during the Sun's first billion years, a period when the Sun was more active and variable than it is today. The Moon's surface is in effect a geological archive of the Sun's early history. Every nuclear fusion reaction in the Sun's core produces neutrinos, subatomic particles with nearly no mass and almost no interaction with ordinary matter. Solar neutrinos travel outward from the core in seconds, passing through the entire mass of the Sun and then through space without significant deflection or absorption. Approximately 65 billion solar neutrinos pass through every square centimeter of Earth-facing surface every second, including the human body. They produce no measurable biological effect and cannot be detected by any conventional means. Their detection requires purpose-built facilities, typically large volumes of purified material placed deep underground to reduce interference from other particle sources. For several decades following the first solar neutrino detection experiments in the 1960s, observed neutrino fluxes were consistently lower than the values predicted by standard solar models, a discrepancy known as the solar neutrino problem. The resolution, confirmed experimentally in the early 2000s, was that neutrinos oscillate between 3 distinct types, or flavors, during transit, and early detectors were sensitive to only one flavor. The missing neutrinos had not disappeared. They had changed into a type the detectors could not register. Resolving the solar neutrino problem required revising the standard model of particle physics to include non-zero neutrino masses, a significant theoretical development prompted by observations of the Sun. Helioseismology is the study of oscillations in the Sun's structure, pressure waves that propagate through the solar interior and produce small but measurable fluctuations at the surface. By analyzing the frequencies and patterns of these oscillations, researchers can infer the temperature, density, and composition of interior layers that cannot be observed directly. The technique is conceptually similar to the way seismic waves are used to probe Earth's interior, Helioseismic observations have confirmed the depth of the Sun's convection zone, mapped internal rotation rates at different depths, and provided independent verification of solar evolution models that predict the Sun's eventual red giant transformation. The oscillations studied in helioseismology fall into distinct categories based on the forces that drive them. Pressure mode oscillations, the most commonly analyzed, are acoustic waves that propagate through the solar interior in 3 dimensions. Surface gravity waves, if they exist in the Sun, would carry information about conditions near the tachocline, the boundary between the radiative and convective zones. By combining observations of many oscillation modes simultaneously, researchers construct 3-dimensional models of the solar interior with considerable precision, allowing detection of structural changes that would take millions of years to manifest visibly at the surface. Every current observation of the Sun, its luminosity, surface temperature, rotation profile, seismic structure, neutrino output, is consistent with a star approximately midway through its main sequence lifetime and undergoing the slow internal changes that stellar evolution models predict. The Sun's future transformation into a red giant is not a theoretical extrapolation from incomplete data. It is the expected outcome of physical processes that are already operating and that have been confirmed by independent lines of observational evidence. The timeline extends far beyond any human frame of reference, but the physics that determines it is well established. In approximately 5.4 billion years, the Sun will leave the main sequence and begin the transition to a red giant. This transition is not a discrete event with a fixed start date. It is the continuation of internal changes already underway, reaching a point at which the Sun's structure has diverged enough from its current state that it can no longer be described as a main sequence star. The transition will unfold gradually, with the Sun's luminosity, radius, and surface temperature changing over hundreds of millions of years before reaching the conditions associated with the red giant phase. The red giant expansion begins when the energy output from shell hydrogen burning becomes large enough to drive the Sun's outer envelope significantly outward. The outer layers, receiving more energy than the equilibrium of the main sequence Sun required, expand in response. This expansion is not fast by any everyday measure. It proceeds over millions of years, but it is substantially faster than the slow brightening of the main sequence phase. As the outer layers expand, their temperature drops and their color shifts toward red, giving the star its classification as a red giant. The expansion of the Sun's outer layers during the red giant phase will not proceed at a constant rate. The stellar envelope will expand and contract in large, slow oscillations as energy from the burning shell propagates outward in waves. These oscillations make red giants variable stars, stars whose luminosity changes periodically as the outer layers pulse. The period of these variations for a star like the evolved Sun would be measured in hundreds to thousands of days. Stars of this type are observed throughout the galaxy as long-period variables, sometimes called mirror variables after the prototype of the class. The Sun will eventually become a member of this category during its late red giant phase. At its maximum extent, the Sun is estimated to expand to between 100 and 200 times its current radius, with some models suggesting larger values. The Sun's current radius is approximately 696,000 kilometers. At 200 solar radii, the expanded surface would reach approximately 139 million kilometers from the Sun's center. For comparison, Earth's current orbital distance is approximately 150 million kilometers. The inner solar system, the region currently occupied by Mercury, Venus, and Earth's orbital path, would lie within or very near the surface of the expanded star. If the Sun expanded to 200 times its current radius without any change in Earth's orbit, the stellar surface would reach approximately 0.93 astronomical units, short of Earth's current position at 1 astronomical unit. Mercury and Venus would be subsumed well before maximum expansion is reached. Whether Earth itself would be engulfed depends on the interaction between 2 competing processes: the outward expansion of the stellar surface and the outward drift of Earth's orbit caused by the Sun's mass loss. Early models suggested Earth might narrowly escape engulfment. Later, more detailed models reached a different conclusion. More recent solar evolution models estimate that the Sun's surface will reach approximately 1.2 astronomical units at maximum expansion, a distance that exceeds Earth's current orbital radius. These models also account for tidal interactions between Earth and the expanded Sun. As Earth's orbit brings it into contact with the tenuous outer atmosphere of the red giant, the resulting drag will slow Earth's orbital velocity and cause the orbit to contract inward rather than expand outward. The mass loss that would otherwise push Earth away is outpaced by the tidal deceleration that draws it inward. On balance, current models indicate that Earth will be engulfed. Based on current stellar evolution models, the Sun's maximum red giant expansion is estimated to occur approximately 7.59 billion years from now. This figure reflects detailed computational modeling of the Sun's internal evolution, incorporating measured values of solar mass, composition, age, and luminosity, along with calculated rates of mass loss and orbital change. As with any projection over such a timescale, it carries uncertainties, but it represents the best current estimate of when the Sun will reach its greatest extent during the red giant phase. The moment of maximum expansion is the peak of a process spanning tens of millions of years, embedded within the red giant phase itself, which extends over a much longer period. The Sun will not rapidly swell to maximum size and then immediately collapse. It will spend an extended time, hundreds of millions of years in total across all subphases of the red giant stage, in an expanded, highly luminous state, undergoing further internal changes before the outer layers are finally shed and the stellar remnant is exposed. The red giant phase is not a brief episode, it is a distinct and prolonged chapter in the Sun's evolution. During certain stages of the red giant phase, the Sun's luminosity is estimated to reach approximately 2,700 times its current level. At that output, the energy reaching the outer solar system will far exceed anything those regions currently receive. Objects in the Kuiper belt and beyond, bodies that have remained frozen since the formation of the solar system, will receive sufficient energy to alter their surface chemistry and, in some cases, to develop temporary atmospheres. The transformation of solar system conditions during the red giant phase will not be limited to the inner solar system. The increased luminosity will have measurable effects at distances far beyond the current orbits of the outer planets. The rate at which the Sun loses mass will increase substantially during the red giant phase. In its current state, the Sun loses mass through the solar wind at a rate of roughly 2 × 10⁻⁴ solar masses per year, a small but continuous outflow. Red giants lose mass at rates millions of times higher, driven by radiation pressure acting on dust and molecules that form in their cool outer atmospheres. This mass loss is not explosive. It is a sustained, slow exhalation that gradually strips the outer layers of the star over millions of years, returning material to the interstellar medium from which the Sun originally formed. Over the course of the red giant phase, the Sun may lose between 25 and 33% of its total mass. The Sun currently has a mass of approximately 1.989 × 10⁻30 kilograms. A loss of 1/3 of that mass represents an enormous quantity of hydrogen, helium, and trace heavier elements dispersed into the surrounding solar system and eventually into the interstellar medium. This dispersed material does not simply disappear. It becomes part of the diffuse gas and dust that fills the galaxy, available eventually to be incorporated into future stellar systems, continuing the cycle of stellar birth, evolution, and death that has operated throughout the history of the Milky Way. As the Sun loses mass during the red giant phase, its gravitational hold on the planets weakens proportionally. The orbital radius of a planet in a circular orbit around a star losing mass increases in inverse proportion to the remaining mass. As the Sun becomes less massive, the planet's orbits expand outward. This effect applies to all planets in the solar system simultaneously. Mars, Jupiter, Saturn, and the outer planets will all shift to wider orbits as the Sun's mass declines. The expansion is gradual and continuous throughout the mass loss phase, proceeding in tandem with the Sun's swelling radius. The outer planets and their moons will drift to larger orbital distances as the red giant Sun sheds mass over millions of years. Jupiter's orbit will expand, Saturn's rings and moons will move outward. The icy moons of the outer solar system, Europa, Ganymede, Callisto, Titan, and others, will migrate into regions receiving substantially more solar energy than they currently do. Some of these moons carry internal oceans of liquid water beneath their ice shells today. Their surface and subsurface environments will change in response to the increased solar energy as their host planets shift outward and the Sun's luminosity rises. As the red giant phase progresses, the inert helium core continues to contract under gravity. The electrons within the core are packed to densities at which they can no longer be treated as a classical gas. Instead, they enter a state governed by quantum mechanical effects called electron degeneracy, in which the Pauli exclusion principle, the quantum rule that no two electrons can occupy the same state, exerts a pressure that resists further compression independent of temperature. The temperature of this degenerate core continues to rise even as it contracts, climbing toward the threshold required to ignite helium fusion. That threshold is approximately 100 million degrees Celsius. When the degenerate helium core reaches approximately 100 million degrees Celsius, helium fusion ignites in what is called the helium flash. In a non-degenerate gas, a temperature increase causes the gas to expand and cool, which moderates the fusion rate and provides a natural control mechanism. In a degenerate core, that control mechanism does not operate. Rising temperature does not cause the core to expand. The fusion rate therefore increases without limit for a brief period, producing a thermal runaway. At its peak, the energy released internally rivals the total luminosity of the entire Milky Way galaxy, on the order of 100 billion solar luminosities, sustained for a matter of minutes before other effects intervene. The helium flash is not a visible event. Despite the extraordinary internal energy release, the luminosity of the star as seen from outside does not increase significantly during the flash. This is because nearly all of the energy produced goes into lifting the electron degeneracy of the core, providing the energy needed to return the core to a non-degenerate state in which temperature and pressure are normally coupled. Once the degeneracy is lifted, the core expands and cools to a stable configuration. The energy of the helium flash is absorbed by the structural change it causes, rather than escaping as radiation. The flash passes without any external signature. Following the helium flash, the Sun will enter a phase called the horizontal branch, during which it burns helium stably in a now non-degenerate core while continuing to burn hydrogen in the surrounding shell. This phase is expected to last approximately 100 million years. During the horizontal branch, the Sun will be somewhat smaller than at its maximum red giant extent. The lifting of core degeneracy causes the core to expand, which reduces the energy input to the shell and allows the outer layers to contract somewhat. The horizontal branch represents a period of relative stability between the extreme conditions of the red giant ascent and the subsequent phases of the star's evolution. During the horizontal branch phase, the Sun will contract to a smaller red giant configuration before undergoing a second, final expansion. Stellar evolution does not follow a single monotonic path toward greater size. The sequence includes periods of expansion followed by stabilization or modest contraction, driven by the successive ignition and exhaustion of different fuels in different regions of the stellar interior. The horizontal branch contraction is a well-documented feature of stellar evolution models and has been confirmed by observations of stellar populations in globular clusters, where large numbers of stars at various evolutionary stages can be observed simultaneously. The red giant Sun will be structurally extreme in both directions simultaneously. Its outer envelope will extend over a volume comparable to the inner solar system, a diffuse, cool plasma hundreds of times larger than the current Sun. Its core will be compressed into a sphere roughly comparable in size to Earth, containing a substantial fraction of the Sun's remaining mass. The density contrast between the core and the outer atmosphere will be immense. The core will be among the densest non-degenerate matter in the solar system. The outer envelope will be so diffuse that what exists in those outer layers would qualify as a near vacuum by terrestrial standards. As the Sun's radius increases during the red giant phase, its surface gravity decreases. Surface gravity falls with the square of the radius. Doubling the radius reduces surface gravity to 1/4 of its original value. At hundreds of times the current solar radius, the surface gravity of the red giant will be a tiny fraction of what it is today. In those conditions, the outer atmosphere is so loosely bound that radiation pressure alone is sufficient to drive mass loss at the high rates observed in evolved giant stars. The star does not need to eject material violently. The combination of low surface gravity and high radiation pressure makes continuous, steady mass loss the natural state. The light emitted by the red giant sun will fall predominantly in wavelengths corresponding to a surface temperature of roughly 3,000 to 4,000 degrees Celsius, a deep reddish-orange color that no planetary surface in the current solar system is exposed to. The quality of illumination across the solar system will be fundamentally different from today. Lower in peak energy per photon, greater in total quantity, and weighted toward longer wavelengths. Objects in the outer solar system that currently receive minimal solar energy will, for the first time in their histories, be exposed to meaningful levels of solar radiation. Titan, Saturn's largest moon, is a candidate for temporarily more hospitable conditions during the red giant phase. Its surface pressure is slightly higher than Earth's at sea level, and it has a dense nitrogen atmosphere with a complex organic chemistry driven by solar ultraviolet radiation and cosmic rays. As the Sun's luminosity increases and Saturn's orbit expands outward, Titan's surface temperature may rise into a range where liquid water could exist transiently. Whether the conditions would be suitable for any form of biology is unknown, but Titan's thick atmosphere and surface chemistry would respond measurably to the increased solar energy of the red giant phase. Europa, Ganymede, and other icy moons of the outer solar system currently maintain liquid water oceans beneath their frozen surfaces, sustained by tidal heating and in some cases residual internal heat. As the red giant sun's luminosity rises and the outer planets drift outward, these moons will receive substantially more solar energy. The ice shells overlying their internal oceans may thin at the surface or partially melt, altering the physical environment of the subsurface ocean above its current state. Whether conditions suitable for the emergence of life could develop during this period is a question that cannot be answered with current evidence, but the physical changes to these environments during the red giant phase are expected to be significant. The character of the solar wind during the red giant phase will be substantially different from the fast, sparse particle stream emitted by the current sun. A red giant's wind is slow, dense, and heavily loaded with dust and molecular material formed in the cool outer atmosphere. It does not drive the same electromagnetic interactions with planetary magnetic fields that produce auroras today. Instead, it carries material outward in large quantities and at relatively low velocities, contributing steadily to the mass being dispersed into the surrounding space. This outflow is the mechanism by which the Sun will shed 1/3 of its mass and eventually expose the stellar core that becomes the white dwarf. The Sun's evolution into a red giant is the standard outcome for stars of its mass and composition. Observational surveys of stellar populations confirm that stars in the mass range of 0.8 to 8 solar masses, the range that includes the Sun, consistently follow the evolutionary path from main sequence to red giant to planetary nebula to white dwarf. This sequence has been documented through observations of thousands of individual stars at different evolutionary stages and through stellar population studies of clusters where stars of known age can be examined in bulk. The Sun's eventual red giant phase is not a theoretical prediction made in isolation, it is the expected behavior of a well-characterized class of object. Whether Earth is physically engulfed by the expanding red giant sun depends on the relative rates of two competing processes: the outward expansion of the Sun's surface and the outward migration of Earth's orbit due to the Sun's mass loss. If the Sun's surface expands faster than Earth's orbit moves outward, Earth will be engulfed. If Earth's orbit expands faster than the stellar surface approaches, Earth will survive outside the star. Early estimates suggested the two effects might roughly balance. More detailed models, incorporating tidal interactions, have generally concluded that engulfment is the more likely outcome. Initial solar evolution models that predicted Earth might narrowly escape engulfment did not fully account for tidal interactions between Earth and the red giant sun's expanded outer atmosphere. As the stellar surface approaches Earth's orbit, Earth will begin moving through the tenuous outer layers of the red giant. That material exerts drag on Earth's orbital motion, slowing its velocity. A slower orbital velocity results in a lower orbit. The planet spirals inward rather than being pushed outward. The same expansion of the Sun that would have provided orbital drift through mass loss also creates the tidal interaction that works against Earth's escape. The two effects do not add, they oppose each other, with the tidal effect appearing to dominate in current models. A 2008 study by astronomers Klaus-Peter Schroeder and Robert Conan Smith, published in the monthly notices of the Royal Astronomical Society, applied detailed modelling of both solar expansion and Earth's orbital evolution to conclude that Earth will be engulfed approximately 7.59 billion years from now. Their analysis accounted for mass loss rates, tidal interactions, and the resulting orbital dynamics. The study remains a standard reference in discussions of Earth's long-term fate. Subsequent modelling has generally supported their conclusion, though the precise timeline depends on assumptions about the Sun's mass loss behaviour during the red giant phase. Whether or not Earth is physically engulfed by the red giant Sun, the planet will be uninhabitable for billions of years before that event. The oceans will have evaporated, the atmosphere will have been stripped away, surface temperatures will have risen beyond any range associated with liquid water or complex chemistry. The planet's geological activity will have ceased. The question of engulfment is a question about the final state of a rock that has already been rendered geologically and biologically dead long before the red giant phase begins. The distinction between engulfment and near miss is meaningful in an astronomical sense, but not in any biological or planetary habitability sense. Earth's oceans are expected to begin significant long-term decline within approximately 1 billion years, as increasing solar luminosity drives enhanced evaporation and accelerates the atmospheric escape of hydrogen. The process will be slow, measurable only across geological timescales, but irreversible under the conditions that will prevail. As atmospheric water vapor increases, the greenhouse effect intensifies, surface temperatures rise further, and the rate of water loss accelerates. The oceans will not drain suddenly. They will thin over hundreds of millions of years until liquid water is no longer stable on the surface across most or all of the planet's area. Earth's plate tectonic system requires water to operate effectively. Water reduces the melting point of silicate rock, lubricates subduction zones, and is incorporated into the minerals of the subducting crust in ways that facilitate its descent into the mantle. Without a sufficient water supply, subduction becomes more difficult to sustain. As Earth's surface water declines over billions of years under increasing solar energy, the plate tectonic system is expected to slow progressively. A geologically inactive Earth would lose the volcanic outgassing that currently replenishes atmospheric gases and the crustal recycling that has renewed the planetary surface for billions of years. The cessation of plate tectonics would disable the carbon-silicate cycle, which depends on the continuous weathering of fresh rock brought to the surface by tectonic activity and on volcanic outgassing to replenish atmospheric carbon dioxide. Without active tectonics, atmospheric carbon dioxide will no longer be regulated by this mechanism. Depending on conditions at the time, the result could be runaway accumulation of carbon dioxide from residual volcanic activity or depletion without replenishment, either scenario removing a critical component of the climate regulation system that has moderated Earth's surface temperature for billions of years. Estimates place the end of conditions hospitable to complex multicellular life on Earth's surface at approximately 2 to 3 billion years from the present, driven primarily by the Sun's ongoing brightening and the resulting decline in liquid water availability. This estimate applies to surface conditions. It does not preclude the continued existence of microbial life in subsurface environments, hydrothermal systems, or other settings insulated from surface conditions. The timescale for the disappearance of a recognizable surface biosphere, one involving plants, animals, and functioning ecosystems, is shorter than the timescale for the complete elimination of all life from the planet. Microbial life on Earth today occupies environments with temperature, pressure, acidity, salinity, and radiation levels far outside the range tolerated by complex organisms. Thermophilic bacteria thrive in hydrothermal vents at temperatures above 100 degrees Celsius. Organisms in deep subsurface rock formations survive on chemical energy with no dependence on sunlight. Halophiles persist in salt concentrations lethal to most life. The capacity of microbial life to occupy extreme environments suggests that as surface conditions on Earth deteriorate under increasing solar luminosity, some microbial life may persist in subsurface refugia well beyond the point at which the surface becomes uninhabitable for complex organisms. During the red giant phase, the elevated radiation output of the Sun will erode whatever remains of Earth's atmosphere more rapidly than current solar conditions allow. Atmospheric escape, the loss of gas molecules to space, is driven by the energy input from solar radiation and the solar wind. At 2,700 times the Sun's current luminosity, the atmospheric erosion rate will be far higher than anything Earth has experienced. Any thin residual atmosphere remaining on Earth at that point will be stripped away over millions of years by the intensified radiation and particle flux, leaving the surface exposed directly to the stellar environment. Earth's magnetic field is generated by convection in the liquid iron outer core, driven by the temperature gradient between the hot inner core and the cooler mantle above. Over geological time, as the planet's interior slowly loses heat, the temperature gradient decreases and the convection driving the dynamo weakens. The timescale for significant magnetic field weakening through this mechanism is not well constrained, but over billions of years, as Earth's interior cools and the solid inner core grows, the dynamo is expected to become less vigorous. A weaker magnetic field offers reduced protection against solar wind erosion of the atmosphere. With a weakened or absent magnetic field and exposure to the intensified solar wind of the red giant phase, Earth's remaining atmosphere, already thinned by billions of years of atmospheric escape, will be subject to direct particle bombardment. The solar wind during the red giant phase is not the fast, sparse stream of the current Sun. It is a slow, dense outflow carrying large quantities of material. The rate at which it strips atmospheric gas from an unprotected planet will be substantially higher than current loss rates. Atmospheric erosion that currently proceeds slowly will accelerate under these conditions. If Earth is present at the boundary of the red giant's outer atmosphere, either because it has not been engulfed or as it approaches engulfment, it will experience tidal forces from the asymmetric gravitational field of the expanded Sun. Moving through the tenuous outer layers of the red giant, Earth will encounter drag that decelerates its orbital velocity. A reduced orbital velocity at a given radius causes the orbit to shrink. The planet moves to a lower, faster orbit closer to the stellar center of mass. The deceleration is self-reinforcing. As Earth moves inward, it encounters denser material, which increases the drag, which further reduces orbital velocity. The process continues until engulfment occurs. As Earth spirals inward through the outer layers of the red giant, its orbital period decreases. The tidal forces acting on the planet increase with proximity to the stellar core. The surface of Earth, already molten under the radiation of the expanded Sun, would be subjected to increasing tidal stress as the inward spiral continues. Tidal deformation generates heat through internal friction, adding to the thermal input from the surrounding stellar material. The planet's structure at this stage would bear no resemblance to its current form: no atmosphere, no surface water, no crust in any conventional sense, just molten rock in an increasingly tight orbit around a star. In its final phase before engulfment, Earth would be a molten, airless body moving on a contracting orbit through the outermost layers of a red giant star. The surface, exposed to both the direct radiation of the stellar interior and the heat of tidal deformation, would be a global magma ocean. No solid crust would be stable. No atmosphere would persist. The planet would continue moving inward until the density of the surrounding stellar material was sufficient to cause rapid deceleration and final submersion into the star. The material that constituted Earth, rock, metal, and the remnants of everything that once existed on its surface, would be dispersed into the outer layers of the Sun. After the red giant phase, the Sun will not end as a supernova. Supernova explosions occur in stars with masses significantly greater than the Sun's, generally above 8 solar masses, which can sustain nuclear burning through progressively heavier elements until iron accumulates in the core and the star collapses catastrophically. The Sun's mass is insufficient for that process. Once helium burning is exhausted and carbon and oxygen accumulate in the core, the Sun cannot ignite the next nuclear fuel stage. Without the energy production needed to counteract gravity, the outer layers will be expelled gradually, and the remaining core will be left behind as a compact remnant. As the Sun exhausts its helium fuel and the outer layers are expelled, they will form a planetary nebula, an expanding shell of ionized gas and dust surrounding the exposed stellar core. Planetary nebulae are among the most visually distinctive objects observable in the galaxy. Examples include the Ring Nebula in the constellation Lyra, the Cat's Eye Nebula in Draco, and the Helix Nebula in Aquarius. Each of these is a former star of roughly solar mass in the process of dispersing its outer layers. The Sun's eventual planetary nebula will expand outward from the position of the current solar system, glowing as its gas is ionized by ultraviolet radiation from the white dwarf at its center. The term planetary nebula is a historical misnomer. It originates from the 18th and 19th centuries, when astronomers using small telescopes noted that these objects appeared as round, disc-like patches of light resembling the visual appearance of Uranus and Neptune. William Herschel, who coined the term, applied it on this basis of visual similarity alone. Planetary nebulae have no connection to planets. They are the expelled outer atmospheres of dying low to intermediate mass stars, illuminated by ultraviolet radiation from the hot compact remnant at their center. The terminology has been retained in astronomical convention despite being misleading. The colors visible in a planetary nebula are determined by the composition of the expelled gas and the intensity of radiation from the central white dwarf. Doubly ionized oxygen emits in the blue-green portion of the spectrum. Ionized hydrogen produces red emission. Ionized nitrogen contributes orange and red tones. The morphology of a planetary nebula, whether it appears as a sphere, a ring, a bipolar structure, or a more complex shape, reflects the geometry of the mass ejection, the influence of the magnetic field, and the presence of a binary companion if one exists. The Sun's planetary nebula will have a morphology determined by its specific rotation history and mass loss pattern. The expanding shell of a planetary nebula typically moves outward at 20 to 30 kilometers per second. At that rate, the Sun's nebula will cross the span of the inner solar system in a matter of decades and the outer solar system in a few centuries. Over thousands of years, it will disperse beyond the orbital distances of the known planets. Over tens of thousands of years, it will fade as the gas density drops below the threshold required for visible emission. Eventually, the atoms of the former stellar envelope will mix into the interstellar medium, indistinguishable from the general population of gas and dust that fills the galaxy between stellar systems. At the center of the dispersing planetary nebula, what remains of the Sun's core will be exposed as a white dwarf. A white dwarf is the endpoint of stellar evolution for all stars below approximately 8 solar masses. It is not a star in the active sense. It generates no energy through nuclear fusion. It is the compressed remnant of the stellar core, held against further gravitational collapse by electron degeneracy pressure, the quantum mechanical resistance to further compression of electron-occupied states. White dwarfs are among the most common stellar remnants in the galaxy, estimated to constitute roughly 97% of all stellar endpoints in the Milky Way. The Sun's white dwarf remnant will be approximately Earth-sized in diameter, roughly 10,000 to 12,000 kilometers, while containing between 50 and 60% of the Sun's original mass. The density this implies is approximately 1 million times greater than water. A volume the size of a sugar cube taken from a white dwarf would contain roughly 15 tons of material. This extreme density is a consequence of the compression of stellar core material to a state in which the electrons are fully degenerate, packed as tightly as quantum mechanical constraints permit, and the normal atomic spacing of matter has been reduced to near zero. Immediately following its formation, the Sun's white dwarf will have a surface temperature of approximately 100,000 degrees Celsius. At that temperature, the dominant emission is in the ultraviolet and soft X-ray portions of the spectrum. The white dwarf will be luminous in terms of energy per unit area, but its small surface area, comparable to Earth's, means its total luminosity will be far lower than the current Sun's. Over time, as the white dwarf cools, its emission will shift progressively toward visible wavelengths, first as a blue-white object, then white, then yellow, then orange-red, following the same color-temperature relationship that governs all stellar objects. A white dwarf produces no new energy through nuclear reactions. The heat it radiates is residual thermal energy stored in its dense crystalline structure, accumulated during the billions of years of nuclear burning in the preceding stellar phases. That stored energy is released slowly through radiative cooling, a process that is extremely slow because the white dwarf's high density means it has enormous heat capacity relative to its surface area. The rate of cooling decreases over time as the temperature drops, making the total cooling timescale very long even for the oldest white dwarfs currently observable. The estimated time required for a white dwarf to cool to the point of emitting negligible visible light, a hypothetical final state called a black dwarf, is on the order of 10 to the 15th power years, or roughly 1 quadrillion years. For context, the current age of the universe is approximately 13.8 billion years, which is 13.8 times 10 to the 9th years. The cooling timescale for a white dwarf exceeds the current age of the universe by a factor of approximately 70,000. The progression from white to yellow to orange to red to dark would take far longer than any timescale relevant to the current state of the observable universe. No black dwarfs exist anywhere in the observable universe. The universe at approximately 13.8 billion years of age is too young for any white dwarf, even the oldest formed shortly after the first stars appeared, to have cooled to a black dwarf state. The black dwarf is a theoretical prediction based on well-established physics of white dwarf cooling, but it describes an object that will not exist for timescales vastly longer than the current age of the cosmos. When the Sun's white dwarf eventually achieves that state, if the universe persists long enough, the context in which it exists will be unrecognizable relative to the present. The outer layers expelled during the Sun's red giant phase and dispersed as a planetary nebula will carry hydrogen, helium, carbon, oxygen, nitrogen, and trace heavier elements into the interstellar medium. These atoms do not disappear. They join the diffuse gas and dust already present in the galaxy, the same reservoir from which the Sun and its solar system originally condensed 4.6 billion years ago. On timescales of millions to billions of years, this material may be incorporated into new molecular clouds, participate in future episodes of star formation, and become constituent atoms of new stellar systems. The material cycle that produced the Sun will continue independently of the Sun's fate. The Sun's eventual dispersal into the interstellar medium is a single instance of a cycle that has operated throughout the history of the galaxy. Stars form from gas and dust, process that material through nuclear fusion over millions to billions of years, and then return enriched material to the interstellar medium through winds, planetary nebulae, and supernova explosions. That returned material is available for subsequent generations of star formation. The heavy elements present in the Sun today, and in the Earth, and in all living things, were produced by earlier iterations of this same cycle. The Sun's death in this context is a contribution to a process that predates its formation and will continue long after its remnant has cooled. The Sun's white dwarf remnant will persist for a period far exceeding the current age of the universe. By the time the white dwarf has cooled substantially, the Milky Way and Andromeda galaxies will have completed their merger into a single elliptical galaxy, a process already underway and expected to reach completion in roughly 4 billion years. The last red dwarf stars in the galaxy, which burn hydrogen far more slowly than the Sun, will have exhausted their fuel and begun their own slow evolution. The white dwarf will outlast nearly all active stellar processes in the local universe, persisting as a slowly cooling remnant of a star that spent the majority of its existence maintaining the conditions that allowed a solar system and at least one inhabited planet to exist. The atoms that constitute the Sun, and those that constitute the Earth and every organism that has ever existed on it, will not be destroyed when the Sun ends its active life. They will be dispersed. Hydrogen and helium will return to the interstellar medium. Carbon and oxygen, synthesized in the Sun's core during the helium-burning phase, will be distributed through the planetary nebula and eventually mixed into the surrounding galaxy. These atoms carry no memory of the structures they were part of, but they remain subject to gravity, to chemistry, and to the same physical laws that assembled them into a star and a solar system in the first place. In time, some fraction of them will be incorporated into new structures, new stars, new planetary systems, new configurations of matter that cannot be predicted from any current vantage point. The Sun that rose this morning has been burning for 4.6 billion years. It will continue burning for roughly 5 billion more before the changes described here begin in earnest. The red giant phase, the planetary nebula, the white dwarf. These are not causes for alarm. They are the standard life cycle of a medium-mass star playing out on timescales that exceed the current age of the universe. The atoms that make up the Sun, the Earth, and every living thing on it have already passed through at least one stellar furnace before arriving here. In time, they will pass through another,